Hello, this is Ralph Alvarado, and welcome to Exploratory Text Analytics. In this video, we're going to be looking at similarity and distance measures, and we're going to use those to create two kinds of cluster, k-means clustering and hierarchical clustering. All right, let's get right into this. So, as usual, in my configuration segment of the notebook, I'm defining some things that I'm going to use throughout the notebook. In this case, I'm defining two OCO objects or lists. The first one corresponds to the index of the TF-IDF table that I'm going to be importing, and the second one corresponds to the ordered hierarchy of content objects of the table after I reduce it. So my strategy is I'm going to take the TF-IDF table we worked on last time. I'm going to take the reduced version, which is the one that has just in the columns, as it were, in the term features, just going to keep the significant terms. That makes things a lot more computationally effective when I start to do these pairwise comparisons. And the other thing I'm going to do is once it comes in, I'm going to compress it so that the bag is not the chapter, which is a kind of a large number to represent in a hierarchical cluster diagram. And I'm going to convert that into a smaller bag, books, to illustrate a principle. You can use any bag size you want for these clustering algorithms, but there are issues then about how to represent them and interpret them once you've done that. We'll get into that. So right now I'm going to import the main libraries that I'm using. I'm importing pandas, NumPy, regular expressions, which I think I had here for an earlier use, but I took out the cell block that used it, but we'll just leave it there. We're also going to import the norm function from NumPy's linear algebra library and the pdist, which stands for pair distance, I think. That's a function that lets you compare a whole set of vector pairs using a particular distance metric, and we'll get into that. Here I'm going to be also using Seaborn as my visualization tool because it has a nice scatter matrix representation, which I want to use, and you'll see that in a second. Yeah, so I'm going to continue from here. So now I'm going to import data. I'm going to import the TF-IDF table, and you can see I'm importing the one called TF-IDF reduced, which is a TF-IDF table that just has the terms that are considered significant. I'm also importing the vocabulary table in case I need to use that. And this time I'm also importing the library table because I want to be able to look at the names of the books that I'm working with in this collection and not simply their numeric IDs. I want to be able to tell, for example, when I cluster this corpus, I want to be able to see where the Melville books are and where the Jane Austen books are. All right, so I import those. First thing I do is I take the library table that I've imported and I add some extra columns to it. Remember that in the raw form it just had this title and file columns, which are a little bit noisy. I simply took the presence of Austen and Melville as evidence for the author being those two and created an author table. And here I have the title column here being generated by a split function on the title string. So anything before the word by with a comma is going to be considered the title of the book. So I end up with this nice information here. I could even lose this column here, book file, if I wanted to, or even book title, because these two things are much more informative. Anyway, now I have my library in a kind of readable format. So the next thing I'm going to do is I'm going to take the TF-IDF table that I imported and I'm going to collapse it. It's a very simple operation. So I'm just going to group it by the OCO that I defined, and you remember up here it's just the book ID. So if we look at the TF-IDF table before it is, and actually let me just run through this for you so you can see what's happening. There's my TF-IDF import, and I'm right here. I'm just going to quickly show you what TF-IDF looks like. There you go, and you'll see that in the OCO we have book and chapter there. All right. Here I'm going to do this. And now I've collapsed this table, and you'll see that it's going to look different. Now it just has a book ID. And what these values are for each feature is the average term significance for all the chapters. in this book. So that is a reduction. Now we could have, in generating the TF-IDF table, we could have chosen book as our bag, but we didn't. But we could do that if we wanted to, if we're creating a pipeline. This works just as well, just getting the mean and using these values. All right, so now we have a reduced or collapsed TF-IDF table, which has already been reduced, as it were, in the column axis by selecting significant words. The next thing we're going to do is create a document table. So remember, in our general model of our general data model for representing text, we had this idea of a doc table, and that table is the table that stores information that relates to the bags, as it were, of the documents in the token table. And here we're just going to create this because we're going to want to add certain columns to this table. In particular, when we do k-means clustering, the cluster assignments are going to apply to the document level, and we'll show you how that works in a second. But it's a very simple operation here. I'm simply getting the TF-IDF table that we just created. I'm resetting the index so that the OCO that's in the index is popped out into the columns, and I'm just grabbing those columns. Let's do this, and you'll see what this does. The doc table now looks like this. We've got the book ID as a column, and then we have this unnamed column here, or this index, which is what we want to use to call the doc ID. And I'm going to go here, and now we have the doc ID, and we have a column for the book ID. So there we go. We have our document table, and we're going to put stuff on the document table as well. And we'll see what I mean by that. Here we have the first thing I'm going to add is a title. So let me go here, and I'm just getting the title as a combination of the author from the library and doing some concatenation of the strings in the OCO. Again, if the OCO had more than one level to it, this would concatenate those items with a dash, and then I'm adding the title to it. And so the result then is this. So now I have two columns in my document table, one of them the ID of the book, and the other one a readable title. This is going to be used as our label for the when we visualize the clusters that we're going to generate. Okay, so far all we've done is imported our tables. We've reduced the TF-IDF table, and we've created a document table that has these nice this extra metadata associated with it, and we'll see what that does in a second. Now what we're going to do is we're going to create some normalized tables. Remember, we talked about normalization, and we talked about how different kinds of normalization lend themselves to different kinds of distance measures. Here I do three kinds of normalization in addition to the non-normalized table, which is the TF-IDF table itself, which I'm going to call raw down below. I'm creating three normalized tables so that we can apply different distance measures as appropriate. The first one, LO, is technically not an LP distance measure or norm form, but we still have it, we still use it. And what this means is simply taking every value in the table, converting it into a Boolean, true or false, and then converting that Boolean value into an integer, 0 or 1. So that just is a binary count table that we talked about. The other two are the L1 and L2 norms. So L1 norm is essentially in Manhattan space, and the L2 norm is in Euclidean space. And you can see that in the first case here, I'm just simply using an apply function to divide each value element in the document vector by the sum of those, and that gives you essentially a probability value. And then here we're using the norm function that we imported earlier, and what that does by default is create an L2 normalization of this row, of the values in this row or vector. So then I have three different tables, and I'll just run this and show you what a couple of these look like. Let's look at L2. There we go. So these are where every value has been basically divided by the sum of the squares, the square root of the sum of the squares of every value in this table. And one way to prove that we actually did that is to do if I take these values, and let me see if this works here. L2, Let me transpose it first so that I can work on a column-wise way. If I do this, square it, and then every value is now squared, and then sum it, should equal 1. Yep, they're all equal to 1. That's how you can tell that you've normalized your table properly in L2 space. You basically re-square everything and get the sum of their values, and it should equal to 1. All right, so now we're going to create a document pair table, and what this is a table where basically it's the Cartesian product of all possible document vectors. So recall that we have a document term matrix, and on one axis we have all the document names, and each document name is associated with a vector. So what we're going to want to do is take every vector and compare it to every other vector, and that's going to result in a single distance value. So that results in a 3 feature or 3 column data structure: the table A, table B, and their distance by a certain metric. So what we're going to do is we're going to create a table that just has all the combinations of A and B, and then we're going to create columns for each distance metric. I'm just going to bind them as we go. And again, you'll see how this works with the example. So let me create this pairs table, and then I'm just going to see what its shape is. And what this results is that this is saying that there are 190 unique combinations of vector pairs. Now, something that's going on here that's worth noting is that what I have done is with this condition here, I've only picked cases where the value of document A is less than the value of document B. What that does is eliminate pairs where the 2 documents are equal, because we don't care about those, because they have a similarity of 1 or a distance of 0. And it also eliminates cases of the same pair but in the other direction. Instead of 10 being compared to 15, we don't want to also have 15 compared to 10. So we get rid of one of those, and so arbitrarily we just pick only the pairs where the first document has a lower number than the second. It works out very nicely. That is also the assumption that this pdist function makes when it generates the list of pairwise distances for a vector or for a matrix that you give it. And so that's why I'm creating this table. All right, so now you can see that we have here document A and document B, and it's empty. There are no columns yet. It's just an index. So let's start adding some content to this table that we've just created. First thing I want to do is compute the city block distance, and I'm also checking the time for these computations because there's some interesting differences here that we can look at. The other thing to point out is that I'm not actually implementing these distance measures in raw form in pandas. We could easily do that. We could create our own functions and use apply methods to apply them to our matrices. But there's I don't think there's any real value in doing that. Understanding the mathematics behind them, as we went over in the previous video, I think is sufficient. And these implementations are obviously very efficient coming from SciPy. So here's how the pdist method works. You pass it a matrix, such as we have, a document term matrix. It expects a tidy matrix of observations by features. And so in our case, it's a document term matrix. And then you specify a distance measure that's appropriate to the matrix that you gave it. So remember, different matrices have different measures that are appropriate, and we'll see that in the examples as we go. So here is a raw TF-IDF matrix, and we're going to use city block distance, which is a synonym for Manhattan. So I'm going to generate that, and you can see that it takes about 2.57 milliseconds. Now I'm going to generate Euclidean. Now I'm going to generate cosine. Here is a Jacquard distance measure, but notice I'm using L0, which was the binary count version of the TF-IDF table. Here I'm going to use dice, which is another set theoretical distance measure on the same table, L0. And here I'm going to use our L1 normalized table, which is a probability type distribution. And I'm going to use Jensen-Shannon. Remember we talked about how information theoretic measures seem appropriate for probabilistic measures in the document term matrix. So I'm going to run that. What's interesting here, though, is notice how much longer this took. So when you're creating a distance pair table from a much bigger table than we're currently using, this can take a long time, and it's a lot slower, orders of magnitude slower than computing, say, the Jacquard distance. Here it doesn't really matter that much. 29 milliseconds is not that big of a deal. But with a larger table, like when I tried this earlier, using the paragraph as the unit, as the bag, it took around 12 seconds. All right, so now we're going to Euclidean 2. And what I'm doing this for is to demonstrate a principle that we talked about, which is that cosine similarity should be the same as Euclidean cosine. They're all distance measures here. This is converted to distance, so I'll call it a distance measure. Cosine distance is going to be identical to Euclidean distance, where the Euclidean distance is operating on a Euclidean normalized set of vectors, and that's precisely what L2 is. And we'll see whether these are the same. So now let's just look at our results. Now we have a table, our pair table, where every column is a distance measure. Next thing we want to do is sort of take a look at these and see how they correlate to each other. Are they really crazy different from each other, or are some of them pretty much giving the same data back? And so let's run Seaborn's pair plot method, which produces a scatter plot matrix. And we can see some things here. First of all, down here you'll see that the cosine distance and the Euclidean distance 2, the second one that I created, which is Euclidean distance on normalized data, you can see that they're linear. There's a slight curve there, but they're pretty much the same. They track each other. So that proves that point. A couple other things. You can see that cosine distance and Jensen-Shannon are roughly linear, correlated. There's a little bit of variance there. And you see a lot more variance between some of these other metrics. All right. So this is one way of evaluating these metrics, is just looking at how much they're related to each other, how much variation they have amongst themselves. And it's an important point to make here, which is that your choice of a distance metric is a hyperparameter. It's something that you make a choice about in your general pipeline of text analytics, and it's going to influence things downstream. In particular, as we're going to see, it'll influence how your hierarchical clustering takes place. It's not going to influence k-means. I'm jumping ahead here, but k-means relies on Euclidean, so you only have one choice there. But this is a way of seeing that there is a lot of variation. In this data set, we don't see, there's not as much difference between them. We just see variance, but there's some real skewing when you compare distance measures when you use a larger data set. Here, I'll just point out a couple. City block and Jacquard has an interesting distribution. Jacquard and Euclidean seem to have almost no correlation. But we're going to evaluate these based on how they classify the content that we have and get a sense that way. All right, so now we're looking at the same data just in tabular form using background shading. And you can quickly see here that the cosine and Euclidean 2 have the same kind of distribution. They progress in the same way. You can also see that Jacquard and Dice, which makes sense, have a very similar distribution. It's less clear what city block is correlated with, and Euclidean, they seem to have some kind of relationship, but then you see there are these big differences as well. This is just thrown in there. It's not absolutely essential for what we're doing. All right, so now let's look at some clusters. First cluster I'm going to do is a hierarchical cluster, and I'm going to import from SciPy the hierarchy cluster library, and just going to give it a short name, and then I'm going to also import PyPlot because I want to decorate my visualization after it's generated. I'm creating a function here which implements this object to generate what you see down below. Just looking at this really quickly, I'm creating a function that takes as an argument a series called sims, and what that is going to be one of these columns up here, like a city block. We can pass the city block column or the Euclidean column or the cosine column. And we're also going to pick which linkage method, which you read about in the Manning and Schutz readings. There are many to choose from, but we're going to stick with ward clustering because it seems to be a standard within text analytics. There are different approaches you can take, of course, but that seems to be a good choice. And then here's a color threshold, and we'll see what that means in a second, and the figure size, which should be self-evident. So what I do is I take the, within this function, I convert that list of the distance pairs into a tree, and a lot of magic goes on in here using the linkage method. There's where my linkage method is actually passed on to this I'm using method in two senses. The method, the mathematical method we're using versus the method of the object. This creates a tree object, and then we're going to pass that tree object down here into the dendrogram method that's built into this object. So this is a side note. It's interesting that SciPy provides a visualization tool, and that's not something that you have built into matplotlib. It's something that's actually built into the SciPy library. We're going to generate some labels because we want to visualize. We don't want just numbers to look at. We want to actually look at those labels, and that's why we created those earlier. So I'm passing the doc title column as a list, as a set of values, which that just basically breaks it down to an array, which has just got one dimension, so it's effectively a list. And then I'm going to create a figure and start adding stuff to this figure. So those are just the arguments. You can look at those. And let's generate some of these. Actually, let me make sure that I run that. There we go. So here we have, I'm using cosine similarity on the hierarchical visualization of the cosine similarity series that we created. And you can see that it did what it's supposed to do. It created two branches, and this is the key here, this big bifurcation that takes place here. And we've got Melville novels over here and Austen novels here, which is really nice. What we also might want to look at is how these particular distance metrics handle the grouping of novels within an author's corpus. And so here we see Pride and Prejudice and Sense and Sensibility, they don't seem close together, whereas they probably should be. We don't see Love and Friendship and Lady Susan too close together. They're the juvenilia. So this doesn't really tell us a whole lot. Here we do see that the two volumes of Marty are clustered together, which is good. So let's look at the Jacquard similarity and see how it handled this task. So it did it as well. It grouped Melville and Austen properly, but it seems to have done a little bit better in grouping together the Austen novels. We have the juvenilia here separated off as their own, and we have Pride and Prejudice and Sense and Sensibility grouped off on their own, and then we have these novels here. That seems to make sense. White Jacket and Moby Dick go together, which makes sense. Won't go into the details there. And then let's look at Euclidean. Euclidean is similar to the first one, cosine, in that it doesn't seem to do a great job in grouping together Jane Austen stuff, but that's fine. It worked on the first task. Let's look at the city block. Again, we can look at these. This one did a good job in differentiating the juvenilia from everything else. You see this nice split right here. That's basically saying these are her younger novels, these are her older novels, and these right here, these, I'm not quite sure how I'd characterize these three versus these three, but doesn't seem like an unreasonable grouping. Pride and Prejudice and Sense and Sensibility certainly go together. And finally, let's look at Jensen-Shannon. Jensen-Shannon, I think, does a great job because it does this nice bifurcation of the juvenilia and the older novels. And it also groups together Pride and Prejudice and Sense and Sensibility together, and it groups these novels together, which I think makes sense. And that's actually fairly similar to what we saw up here. So that's it. That's what hierarchical clustering does. And looking at this this method here, you should be able to implement this pretty easily. You can just cut and paste this and use it in your own notebooks. All right, so now let's look at k-means clustering, which works differently. We basically pick how many clusters we want to have. Notice these in this clustering, we don't pick how many clusters. It naturally kind of discovers them, which is one of the great advantages of hierarchical clustering. So you can see that it came up with 2. In all cases, it came up with 2 clusters, which is what we expected it to come up with because we have 2 completely different novelists. So we've given it an easy task. So that gives us a clue. Let's use k-means and let's ask it to pick 2 clusters and see if it works. So here I have some text here describing what I said earlier, that k-means is essentially a Euclidean operation. You don't pick your distance measures like you do with hierarchical. You stick with Euclidean. In fact, you don't have a choice. It's just going to use it. So here we're using scikit-learn's cluster library and importing the k-means method from that. And here we go. We're going to pick just 2 clusters. And what I'm going to do is run the k-means fit predict method for each one of the matrices we generated earlier, the raw, the L0 normalized, which is just the binary matrix, the L1 normalized, which is the probability matrix, and the L2 normalized, which is the Euclidean matrix. And each one of these is going to predict a set of a y value, we're going to call it. It's going to assign one of 2 values, since we only picked 2, to each document in our document table. And so I'm just going to treat these as columns, and so we can keep accumulating them and compare them. So let's run this. I'm going to import that, choose my clusters. You can see that's very fast. And I'm going to run it here. And just pay attention over here and realize that the 0s and the 1s don't translate across columns, because each time we run k-means clustering, it just arbitrarily picks 0 and 1. But we'll notice that just like the hierarchical, it was able to figure out the difference between Jane Austen and Herman Melville. Each one makes a distinction between Austen and Melville. So the raw one, Austen is 0 and Melville is 1, and so forth. Now what if we change this up a bit and say, you know what, we want to use 4 clusters. And what that's going to do is we want it to be able to differentiate between Jane Austen and Melville, but maybe find some anomalous novels in each corpus. It's not going to do the nice thing of grouping the groups. We're just going to see 4 separate groups, and we'll be able to tell that 2 of them go together because they both refer to the same novelist if our clustering goes according to plan. So let's run this, and here we see the result. So let's look at the first case. In the case of the raw TF-IDF data, it got all of Jane Austen into category 0, and in category 1 it includes all of Melville's works except for 2. Now the raw table was able to pick out the k-means clustering algorithm applied to the raw table was able to pick out 2 what we might consider anomalous novels. So Pride and Prejudice stands out for some reason. That's interesting because that's her greatest novel. And then we have Melville's Marty, Volume 2, which is regarded as anomalous. But you'll notice that the different count vectors produce different results. And we should probably disregard the L0 and L1 because they're not Euclidean space. I'm thinking. It's not clear, whether these results are meaningful or not when you're sending this kind of data to this algorithm. But we can see the results for these in any case. So we'll see that in using the binary count matrix, it assigned a category 2 to Pride and Prejudice, Pride and Prejudice and these novels, which makes sense. And it singled out the juvenilia, which is interesting. It said, oh, Lady Susan and the earlier works are in group 1. So it figured out the juvenilia of Jane Austen as opposed to her other work. Interestingly here in Melville, it groups all of Melville together, but it figures that the Piazza tales are distinct. And you can, continue this exercise in the other columns. Now, the point I want to make here is that you have 2 completely different ways of clustering this corpus. And in each case, you have variables, parameters that you can change to influence the results. The one thing that's constant in both, regardless of the choice of clustering and the choice of parameters, as we can see, is that they all get the most basic task right, that of distinguishing between Melville and Austin. But we see a lot of variation in how these clustering algorithms pick finer grained clusters. And we know that there are finer grained clusters because things naturally do fall into different groups, such as, Austin's younger work and Austin's older work. The question is, why are some methods finding some distinctions and as opposed to other distinctions that other methods are finding? And is it just random? Are we just looking at tea leaves? It's an important question in this field. Most importantly, what we want to do is figure out which methods are the best at coming up with the groups that make the most sense to us based on the research questions that we have. And that's the salient point here, is that ultimately it's your research question that will guide your choice of a distance metric and clustering algorithm. But also, as a final point, we're not doing supervised classification. We can, but we're not doing that here. So our method of confirming our results has to do with invoking our domain knowledge of the field. And here I've invoked some basic knowledge of the work of Jane Austen, for example, to be able to tell what her younger novels are and her older novels. But ideally, you could bring to bear deeper knowledge and pick methods that seem to be coming up with the results that are in line with what you know to be the case. Of course, if you're doing this in a scientific mode, you want to do that systematically, using there are different methods of getting different people's opinions to converge based on certain kinds of metrics. Anyway, I'm going to stop right there, and I hope that is helpful.